I'm so happy to introduce you today, Rachel. Rachel is a full stack um, generalist and a web specialist at Airtable with 6 years of professional experience. Her passion for best practices and inclusive development pushes her to make an impact at her company and the industry as a whole. She has led the creation of multiple new web services that are visited more than 100,000 users per week and focus on SEO, ally, and testability. She loves writing blog posts or giving talks internally and externally to share her learnings. So, without further ado, Rachel, I'd love for you to take over. Thank you.
Thank you so much for that intro, Mackenzie. And hello, everyone. My name is Rachel Church, and I'm a software engineer at Airtable, and I use the pronoun she and her. I know it is kind of the end of the day, so hopefully you're still awake for this. Today, I want to talk about code debt. It's a term that most of you have probably heard about, but it's often misrepresented and has become the software engineering boogeyman that's always lurking around the corner. So I want to disambiguate code debt a bit, show some research around it, and present some actual ways that developers can dig ourselves out of it. So many of my slides will have citations of the research papers and the data at the bottom, and I'll also have all of the resources at the last slide, and I'll leave some time at the very end for questions, but please feel free to add your questions in chat as we go. So what we're going to be looking at today is a 3-step program to address code debt. The first step is raising awareness of what code debt is, how it happens, and why it's important. And after this talk, hopefully you can go back to your teams and spread this knowledge to engineers and non-engineers alike. The second step is identifying code debt within your own code base. And this step is much harder, but luckily we have 30 years worth of research and books we can lean on. And the third step is to manage the debt explicitly by tracking debt-related tasks and addressing issues as part of the normal development cycle. And that's right, this is not a one-time thing. Addressing code debt is ongoing and needs to become part of the company culture. It's like if you had a garden and you let the weeds take over to the point that became a big problem, it'd be very difficult to have a healthy garden. Instead, we want to have a schedule and we want to tend the garden daily or weekly. Addressing the weeds is a part of the process, and it's not something we do only when we have to. So the debt metaphor was introduced in 1992 by Ward Cunningham, who is this smiling gentleman here, and he's the co-author of the Agile Manifesto. And it's rather amazing to me that the software engineering term was introduced 30 years ago, but it's something we're still researching and figuring out today. Cunningham stated that although introducing not quite right code can speed up development, it's just like a loan. It incurs interest over time in the form of more bugs, more time fixing obscure issues, and more time required to comprehend the code. But the way to pay off the debt is by refactoring the code to be in some better state. So I just introduced 3 very subjective things: not quite right code, the cost of code debt, and some magical better state. And I bet everyone here has a different definition of each of these 3 things. So how are we supposed to dig ourselves out of code debt if we all have different understanding on what that even means? And so this is what I hope to disambiguate today. All code is some liability, and so all code has a cost associated with it. Code will always require some level of maintenance, testing, and documentation. So when I say code debt, I'm specifically referring to the additional efforts required to accomplish that same task. So for example, if you're upgrading a package that is deprecated, that's not code debt. That is just normal maintenance work in a repo. But if the code is structured poorly and it requires 2 weeks instead of 1 to upgrade the package, then that is the interest payment of the code debt. So at some point, a developer had a short-term need that drove them to structure the code in one way that made it more difficult to upgrade that package later. This had some long-term cost, which we referred to as code debt. So restructuring the code in a way that makes it easier to change, maintain, and test reduces the long-term cost. Therefore, it reduces the code debt. And this is when we start looking at some data. In 2018, Stripe surveyed more than 1,000 developers and 1,000 C-level executives and found on average about 33% of engineering time is being spent addressing technical debt around the world. 1/3 of all developer time is reportedly spent trudging through difficult to work with code. In the same survey, senior executives reported that one of the biggest potential threats to their business was lack of developer talent. The report argued that the real problem may not actually be the number of developers available, but rather how productive those developers are able to be with the time that they have. And the developers who responded to the survey were far more aware of the additional time being spent on technical debt than leadership. And this indicates that companies may just be blissfully unaware of how much technical debt is really costing them. Code debt affects the entire company. It's a lot easier to address when everyone's aware that it exists and that it's really a problem. And if leadership thinks the problem is lack of developers, they're just going to keep hiring, and it doesn't really solve the underlying problem, which is that code debt is slowing down development and preventing developers from producing their best work. So imagine this. Imagine there's some back room of hardware and your manager asks you to find a piece of hardware, trace the wires coming out of it, and then add a new wire. It sounds like a simple task until you go into the back room and see this picture. The short-term solution would be to brute force it and to finish your task without changing anything. But what if instead it was the second picture? Which scenario would you rather have? Which one is easier to understand and maintain? And code debt costs more time and effort for exactly the same reason. In both of these images, the behavior and functionality may be exactly the same, especially to everyone else outside of the room. But if we keep adding more code on top of it, eventually we found ourselves in a hole that's really hard to get out of. Developers dread working with this code, more bugs pop up, and it becomes harder to hit deadlines. And we've all felt this to some extent. So the other cost I really want to talk about is motivation and that feeling of dread you get when you're working with code debt. The additional effort needed to complete tasks slowly chips away at developer motivation and morale. Code debt makes it harder to produce high quality software, which makes it harder for developers to feel like they're doing good work and meeting expectations. So I want to prevent companies from looking at code debt from purely a product or performance perspective, but also a cultural one. Code debt has been shown in research to reduce employee motivation, which has long-term ripple effects throughout the code base, even when the developers are not directly working with code that has code debt inside of it. But there's a bright side. On the same study, they found the reverse to be true as well. The process of managing code debt as part of the normal development process doesn't just prevent morale loss, it actually boosts it. So removing code debt brings a sense of progress, continuous improvement, and shared learnings across the team, which increases motivation. For anyone out there who's tended a garden before, there's something incredibly satisfying about pulling weeds out, then stepping back and just seeing a clean row of the garden afterwards. And that's kind of that same feeling. So the right culture and code debt preventative mechanisms reinforce one another. Less time wasted on code debt increases productivity and morale, which then feeds back into a healthy culture, which helps prevent code debt in the first place. So far, I've talked about how code debt is created in the broad sense, but in 2015, Michael Tofano and Fabio Palomba conducted an empirical study on the change history of 200 open source projects to answer the question of why and when code debt is created. So here on the screen, I have 3 common assumptions that we make about when code debt is introduced, and I want you all to guess in chat which ones are true and which one are false. So the first one is that code debt is introduced slowly over time as the code base grows. And what do you think? Is this true or false? Waiting to see stuff in chat. True, 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 true. Wow, overwhelming true here. Actually, this is false. This one tripped you guys up. Developers have a tendency to believe that writing new code from scratch produces clean code, and it's the other developers that come in later and pile code on top that introduces code debt. Researchers found that code debt's actually more likely to be introduced when writing code from scratch. And if you think about it, this kind of makes sense because when there's a clean state, the author has more flexibility in how the code is architected, which presents more opportunities for design problems. When working on top of code, you're actually kind of restrained to the existing design patterns to some extent, and unless you kind of go through and refactor that code. So what about the second assumption here? The second assumption is that code debt's more likely to be introduced right before a deadline. Is this true or false? True, 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 true. Yep. Sorry, that kind of sneak peeked there too. This one is true. Researchers found evidence that in open source projects, when developers have a higher workload, they're more likely to introduce code debt compared to developers with a lower workload. So between these two first assumptions, we know that proper planning and accounting for the time to meet a deadline is critical to preventing code debt. Now, our last assumption here is that developers who are new to a code base are more likely to create code debt than developers who have experience working in the code base. Which one, true or false? False, false, false. Yeah, okay, I thought this one was gonna be the most contentious, but looks like you guys got it. Researchers found that newer developers are actually less likely to create code debt. This may be because experienced developers tend to perform more complex and critical tasks, which would make their commits more prone to introducing design problems. So this means that it is everyone's responsibility. to help prevent code debt. It doesn't matter if you're experienced or earlier career, we're all in this mess together. But what happens after code debt is already introduced in a repo? The research seems to suggest that poorly designed code persists in a code base for long term after being introduced. A 2010 study of change history of 2 open source projects found evidence to support that almost 90% of code debt remains in a project until the very end. This implies that engineers are not spending time to remove code debt. And the study found that code debt was often removed not by targeted refactoring, but as a side effect of other code changes. A 2017 study provides supporting evidence for this theory, and in their survey, they found that less than 8% of engineers say that they address code debt during dedicated refactoring. Now, to make matters even worse, a 2019 study found that a quarter of code debt is contagious, and this means that it forces developers to add more code debt on top of that. And this forms a snowball effect. When code debt exists in a repo, it has a tendency to start growing and accumulating more until those design issues are addressed. So the takeaway here is that regardless of preventative measures, there needs to be some kind of explicit management of the debt after it's introduced so it doesn't continue to grow out of hand. But maybe it's about time we start defining what not quite right code even is. So I want to start off with, have you ever opened up a code file and started poking around, just had this feeling that something wasn't right? It could have been the structure, how many methods there are, or you might not even been able to really put your finger on what was wrong. Well, you might have stumbled upon a code smell, and it's just a hint that there's an underlying issue. Now, code smells aren't bugs, they're just hints that there could be an underlying issue. And if you get the feeling that something's messy or wrong, your intuition might be trying to tell you something. But something I want to point out, I was kind of explicit with my image choice here, is most blogs or presentations on code smells use images of bad smelling things like trash or cheese. But I really dislike that symbolism because code smells aren't inherently negative. They're just sniffable hints that there might be a problem, but it could also mean that you just stumbled upon code in a style that you're not familiar with. But if you were to investigate that code smell, you might be able to identify an underlying anti-pattern. And an anti-pattern is a common pattern that is inefficient or counterproductive and proven to be bad. And these two concepts often get overlapped and confused, but they both contribute to code debt. But are you ready for my hot take? I love code smells. Developers at all experience levels can detect them, even if they don't have the knowledge to evaluate if they're a real problem or not. They spark discussion, investigation, and just team learning. So regardless of if this code smell turns out to be a real issue or an anti-pattern, or just maybe just a style of code you haven't seen before, the correct approach to detecting a code smell is curiosity. But we are all familiar with this term code smell because of the work of these 2 men from the 1990s. There's actually a very explicit and identifiable list of named code smells. And in their book on refactoring, Martin Fowler and Kent Beck introduced 22 distinct code smells. The developer community has continued to add a few code smells and group them, but the original 22 smells are very applicable today. And developers can and should use code smells as indicators to help trace code debt and detect issues before they snowball. As we already discussed, a quarter of all code debt is contagious, so it's better to identify it when it's still small before it really starts to grow and accrue interest. And research shows that code smells are a good indicator of refactor opportunities. They have a 35% higher hazard rate than files with no code smells. Now we are on our second step of addressing code debt, identifying the code debt itself within your repo. And one objective way to identify it is with the use of code smells. And I mentioned there's 22 classic smells, but what if I asked you to name 3 code smells in chat right now? This is a term that we have all heard, but can you even name a couple smells? There's kind of different names for different code smells, but they're very well documented and they've been used across blogs, books over the last 30 years. Lisa, spaghetti smell, yeah, I'm going to mention that in a second. Inconsistent variable names, naming of variables, yep. Data class, that's a good one. Okay, so a couple repeating code, yeah, duplicate code, that's definitely one. And it's surprising to me, like how researched code smells are and how everyone's aware of the term code smells, but people really don't know the name. And so here's the actual list of the 23 classic smells. There was actually dead code has been added by researchers since Fowler's original list. This is a grouping of code smells by statistical relation introduced in 2003 at the Conference of Software Maintenance. And if the code smell you were able to name was spaghetti code, then you're not alone. That's actually one of the most common named code smells. but notice how it's not actually in this list. Spaghetti code represents code that is lacking structure, and it's kind of just a mix of all these other code smells. Some of you might be asking why it's even valuable to be able to name a code smell, and you've gotten this far without being able to know their names. But my answer to that is it provides common language that allows all of us to be able to discuss design decisions and best practices. It takes something that's typically subjective, like a feeling that something's wrong in the code, and it grounds it in something more objective. And so if you were to go to your manager and say you want to spend a week refactoring a feature because it was gross, it's going to be really difficult to get that buy-in. You might also make the code author feel bad that you don't like their code. Instead, if you're able to disambiguate what in the code could be improved, and you could share documentation or research on how that could contribute to bugs, cognitive loads, productivity, etc., it would be much easier to have a discussion and prioritize that as a team without making anyone feel bad. For each of these code smells, you can look up what they are and why they become a problem. And I really like the website refactoring.guru, which I have listed in the footer. It's based on Fowler's book on refactoring, and it provides very clear and concise descriptions of each of these code smells. So we only have about 15 minutes left, so I'm only going to be able to talk about a few of these. And I want to start with the code smell duplicate code, which is one that some of you also named. It is one of the most common smells identified during code review, and Fowler believed it to be the #1 of all code bad smells. So something cool about modern IDEs and static analysis tools is they can sometimes detect duplicate code. This smell is easier than a lot of the other ones to recognize, and it's relatively straightforward to address because it's in this category called dispensables. And this category is code smells pertaining to something unnecessary that can just be removed from the code. Now, when asked what code smells are the most concerning, developers typically point at code smells that are related to size and complexity, namely large class and long method. Both of these smells are just as they sound. It's just classes and methods that are doing too much. And research reinforced developer sentiment to support that these smells are some of the worst out of all of them because they significantly increase error proneness and they decrease comprehension. These are in the category of bloaters, which contain smells that risk code growing so large that you can no longer effectively handle it. It's kind of where spaghetti code would belong. I bet if you found a file in your code base that has an above average number of lines, you could probably find an example of at least one of these bloater code smells. And when Fowler introduced these code smells, web components really weren't a thing, but this pattern I also find all the time in React or other web components. It's really easy to make a React component that just gets really big and has a long parameter list. Now, the last code smell I want to talk about is comments. And this one I really want to deep dive on. I chose it because it's easy to recognize, but it's very counterintuitive, misunderstood, and often just plain ignored. Developers often overlook it despite the fact that research has shown that it has a high correlation with bugs in code. In fact, research suggests that well-commented methods are about 1.6 to 2 times 8 times more likely to be faulty. Now think about the last time you wrote a really nice detailed comment in your code. Why did you create that comment? Most likely you had really good intentions and you realized the code wasn't intuitive or obvious. So you tried to improve the readability by leaving a comment to explain what was happening or how to utilize the method. Comments can work in a way to kind of deodorant or mask the smell of complex or low quality code. And this doesn't mean don't write comments. Please still write comments. But comments should explain why something exists, not the what or how. Good code is really self-documented, and good code is written in a way that is intended to be read by other humans, not just the computer. And let me show an example. So here is a relatively small function that takes a 2-dimensional array that represents a grid of garden plots and some amount of water. So based on the comment, we can see that the water amount is distributed among all of the different garden plots within the array. So notice how there's almost as many comments as there are lines of code. This is our code smell. It's really easy to see this just at a glance that something might be wrong here. But code smells aren't inherently bad. You have to look a little bit deeper to determine if there's actually an issue. And spoiler alert, my talk is on code debt. So yes, this is an issue here. And we are going to spend some time to refactor this. But similar to how a lot of folks don't know named code smells, a lot of folks don't know that there's actually named refactoring recipes. That's actually what Martin Fowler's book on refactoring is. It's a recipe book. And if we define refactoring, it's the process of changing code without changing its behavior. And so Martin Fowler's book includes all of the named code smells that we listed, and it shows you for each of those code smells, the different refactoring techniques you can do to fix it. And modern IDEs such as VS Code and IntelliJ even have built-in tooling for some refactoring methods that will do a lot of that work for you. So if we were to look up the code smell comments, it would see that these are the 4 named refactoring techniques we could use to fix this. And Martin Fowler's personal website, refactoring.com, will actually list all of the different refactoring techniques. I'm only going to demonstrate these 4, but I highly recommend you make a mental note of this site so you can reference any of these refactoring recipes for free later down the line. So going back to our code example, we can follow the if-then logic of the comments code smell as defined in the refactoring book. And the first thing we're going to look at is we're going to see if any of these comments is explaining a complex expression. If so, we can remove the need for that comment by just extracting that logic into a bite-sized chunk with a logical variable name. And so this technique is called extract variable. In other words, we're looking for lines of code that we wouldn't be able to understand without the comment being there. So on the first highlighted line, there's some magic 128 number that we're multiplying by, and we can only tell from the comment that that number is being used to convert the amount of water to ounces. And on the second highlighted line, we're using the output of the first line to somehow get an average. And it looks like we're dividing by the number of rows multiplied by the number of columns. And although you could probably figure out what this is doing, it's just adding more complexity to this function that's kind of unnecessary. So we're going to use extract variable to refactor and remove the need for these comments. And so all we did is we took that magic 128 number, we put it into a variable. Now it's a lot easier to see, okay, that is the conversion between gallons and ounces. And I also renamed the variable to ounces of water. This is actually another refactoring technique called rename variable. No joke, Martin Fowler really did make a recipe for everything here. And then on the second line, we extracted the garden plot count into its own variable. And so now it's a lot more clear how we're getting the average water calculation. And the water garden method here just became a lot easier to skim and understand just by doing that. And we didn't really need those comments after all. The code can kind of speak for itself. But the next thing we want to look at is see if there's any comments that are explaining a logical grouping of code or some section of code. And for this, we can use a refactoring method called extract method. Now, this is the most common refactoring recipe, and if you're only to remember one, it should be this one. Extract method is used in a lot of other code smells as well. And it's kind of as it sounds, we're just going to take this logic and put it into its own method. So the logic to water all of the plants in a row, we put in its own method, which is named and it improves readability. This is a pretty small example. I had to fit everything on one slide, but just imagine for me that the logic and lines of code here are a bit longer and a little more complex. I don't want you to walk away thinking that the solution to code debt is to create a lot of really small modules. That doesn't actually improve readability all the time, and that extreme would also introduce code debt. But from this example, hopefully you can see how the for each loop over the rows is now really easy to read just by skimming it. And so it's just easier for humans to understand what's going on and not just the compiler. The next thing we're going to look at is to see if there's any comment explaining what a method does. And so ideally every class, method, or component should only have one responsibility, and it should be named something that represents that one thing. If you have a really long comment explaining everything the function does, you might have a bloater code smell, such as a long parameter list or long method code smell on your hands. For this example, it looks like without the comments, it isn't very clear how the water is being passed in and how it's being distributed across all the garden rows. We also don't really know that the water amount is in gallons without reading the comment. And so we can use the terminology from the comment itself to rename that method to be more clear. So just by saying distribute water to plots, now with the combination of the name of the method itself and the name of the arguments, it's a lot easier just to like read through and understand what this is doing. It also has the added benefit of once we're using this method elsewhere, we can see what it's doing. Our last refactoring recipe that we can try to apply is called introduce assertion. So if comment is explaining a rule or a specific state that the data needs to be in order to work properly, then we can add an assertion statement into the code itself. In this example, we're assuming that the passing gallons of water will never be negative. You can't really take water out of the ground. So in JavaScript, we have this underrated console.assert statement, and it can log an error to the console if the statement's evaluated to be false. Your future self will thank you because now the code will tell you if the assertion's ever broken. It doesn't require a human to read this, and it takes a lot of the burden off the developer to have to read the comment. And if you want to not display that error message within a customer-facing product, you can instead just assert with a logging tool or wrap the assertion in a development-only check. But now that we've done all that refactoring, going back to our original code here, just for reference, and compare that with our after refactoring, notice it's the same exact number of lines, but the one on the right is written in a way that's intended for humans to read and understand, even without comments. The code kind of speaks for itself. Any existing unit test should still pass, and we have this water garden row helper function that we can now test in isolation or reuse in other places. And please do not walk away from this talk telling you that Rachel told you to never write comments. Comments are still good, but they should always be answering why. So for example, we could have added a comment explaining why the console assert is needed. We could say something along the lines of, water can never be negative because we can't remove it from the ground. That's a why comment, and that's still good. This is a little bit of a contrived example, but hopefully it gives you a general idea of what refactoring looks like and gives you an idea of how to take a code smell and look up refactoring recipes. This brings us to our last step in the 3-step program, managing and preventing the code debt. It doesn't matter how well your awareness is in the company, doesn't matter how much you've identified the code debt, you need to have a plan in place to continuously manage it and prevent it from snowballing. According to the Stripe survey we looked at earlier, code debt and maintaining legacy systems are some of the main reasons that developer productivity is hindered. But of the surveyed developers and executives, only a small percentage of companies even had a process in place for managing that code debt. Just like financial debt or tending a garden, reducing code debt requires a plan and a schedule, and it doesn't work if you try to do it all at once. So if we know that code debt is going to occur naturally, then it makes sense that tracking it also needs to become a part of the natural track or the normal tracking process. If you were to categorize your backlog into one of these 4 buckets here, what percentage of your backlog would be tech debt? Probably that most of the attention would be on new features, followed by bugs, and that's because these are the most visible types of tasks. Then you might have some tasks in your backlog related to infrastructure change that improve performance or reliability, but what's lacking in most backlogs are the tasks that address code debt. These are the tasks that are the most invisible to non-developer stakeholders. And developers feel the cost of code debt first, and we know the implications best, so it's up to us to drive these discussions and communicate the value. Now notice how I'm saying us. This is my call to action here. Don't expect your manager, your designer, your product manager, or even other developers to drive this. If you are aware of tech debt, it's up to you to bring awareness to it and explain the positive value that fixing it can have on the company. And here's some data to make that discussion a little bit easier. A 2020 study compared the amount of time it took engineers to add a new feature and remove a bug inside of code that contained code debt. And then they compared that to the amount of time it took to perform the same exact task, except they refactored the code first to remove that code debt. And they found on average it took less time to refactor the code first before adding the new feature or removing the bug on top of it. If there's a part of the code base that is stable and doesn't get touched very often, then there's no value in tossing that code debt immediately on top of your backlog. The best time to address code debt is before adding new features on top of it. But what about code debt projects that are really large and take a lot of time to fix? When executives hear that the engineering team needs a month or more to refactor something, they might just see a big time sink that isn't being spent on feature development. And while code smells may be easy enough to address within a small team, or when they don't take a lot of time, you really do need high-level leadership support to put a lot of time into a larger refactoring effort. You need to align the entire organization on the shared long-term value of that. And it's kind of an all hands on deck kind of problem. And this is explaining a culture shift. The process of aligning an entire team or an entire organization is shifting the culture. And Yvette Pask, the prior CTO of Meetup, she found success in rebranding the term technical debt to continuous product health. It takes some negative debt and it reframes it into a positive product health. But it also adds the word continuous, which makes it impossible to ignore that it's a category of task that's ongoing and every day. continuous product health is something that anyone can understand and anyone can really get behind. And this is very important to gaining leadership support. It's hard for leadership to understand what code debt means if they're not technical, but everyone can really understand continuous product health. And engineering teams need leadership support in order to get the leverage to dedicate time and resources. And at Airtable, we have something very similar. Airtable calls this engineering excellence, and this is our version of continuous product health. Everyone in a company is already oriented around building great products, improving the customer experience, and we just need to draw that connection between code debt and how we meet these goals. In this screenshot here, this is the Airtable product, and this is where any employee within Airtable can get information on the ongoing engineering excellence initiative. And the objectives of our initiative is to, 1, increase developer velocity, deliver higher quality products to our customers, and improve the health of our code base. We define success as engineers feeling empowered to invest time in engineering excellence work, feeling like it's valued and that they can allocate time towards that, and engineers expressing a growing feeling that they're more productive and they can ship higher quality products faster. And this is just a grassroots effort within Airtable where representatives from each engineering group have come together to drive work streams to shape the engineering excellence culture, the framework, and the technical foundation. And leadership understands the implications of code debt and the value in prioritizing it alongside feature development and other type of work. So it's just kind of a collaboration of different teams coming together to talk about this and get leadership support. More granularly, here's a screenshot of an Airtable base where each team is keeping track of their different technical debt projects, their estimated impact, priority, and the amount of engineering effort it would take to address it. And projects are prioritized based on the impact the project would have on different quality metrics. And these metrics could vary from the customer impact, the code quality, to test coverage. Each team is kind of empowered to identify and address problem areas within the code that are affecting them. And having it all here in one centralized location increases awareness and discoverability across all employees. I can see what other types of tech debt projects other teams are working on, and if I need to collaborate with other teams to fix an issue, I can feel empowered to do that. And this really shows how having the right culture in debt management is a prosperous cycle. And for all of you that don't have this at your companies, it's never too late to start. Hopefully you gain some knowledge that you can take back to your teams and organizations to spread awareness of continuous product health. And hopefully it helps to tend the weeds within your own code base. Again, my name is Rachel Church, and this is my Twitter handle. I would love to hear about any successes or failures that you have had with code debt, and if there's anything you particularly enjoyed or even disagreed with during my talk. I'll put a link to my slide deck there on Twitter later today, so you can access all the research and other sources that exist here on the next slide I'll go to in a second. Thank you guys for your time. This was a lot of fun.
Thank you, Rachel, for all of these strategies, for sharing all of these strategies with us. Thank you, everyone. And let me check if we have some questions from the chat. And I think one person asked about if the slides get shared with us.
I'll post them on my Twitter later today. I don't know what other people are going to do, although other presenters, I might follow suit if there's one centralized location that Women Who Code is using to present slides, but I will share them out.
Yes. Remember, the recording will eventually upload on the YouTube channel, and you can visit the YouTube from Women Who Code. And another question is having a lot of these considered a code smell?
Having a lot of divs considered a code smell? It depends. So when Fowler created the code smells, a lot of the HTML web components isn't really what he was targeting. He was more looking at like C++, Java-esque code. A lot of divs, though, is probably an accessibility concern. And I say that those code smells and accessibility are both code debt. So kind of, for lack of a better answer.
Sure. We have another question. Is How long do you think it's too long for a function that might need refactoring?
It really depends. There is no strict answer here. Personally, I think a sweet spot with methods is for a method should only be doing one thing and one thing well, and about 11 lines of code in JavaScript, I think, is a good metric, but also other languages that don't have curly braces might be less or more. It just, you can ask yourself, is your function doing one thing or is it trying to do multiple things?
Thank you, Rachel. And the last question is, how do you use code smell names to have conversations when the people you are talking with are not yet familiar with that vocabulary either?
Great question. I think it's just a way to start raising awareness. So if you're doing a code review, for example, and there's something that you feel like could be improved, it's a way to ground the conversation in something objective. You can just simply link the resource and say how the code small applies to that code there and how it could be improved. It's just a lot harder to have a subjective conversation just saying this can be improved. Just by having the name, you can at least provide resources and start that conversation. Thank you, everyone. Thanks for joining.